A DC track circuit is for telling if there is a train and where it is. It works not by telling you that there is a train, nah, that would be too obvious, wouldn't it? Nah, but by proving that there's no train for any particular section of track. You see, it can't absolutely prove that there is a train.
No, it can't do that for certain, no. See, if there's a fault, it gives the same indication when there is a train as when there isn't one. So the way it works is by telling you when there is no train on the track circuit. See, that way you know it's safe. It's a fail-safe system.
If the track circuit is clear, the relay will pick because the circuit is complete.
Yeah, you know that signal you saw went back to red? Well, that's because the relay dropped.
Sure, and that's because there was a train on the track. The wheels and the axles of the train short-circuited across the rails. That stopped the relay getting any current. That's why the relay dropped.
Now, in the signal box, the track will show occupied. The signalman will know there is something on the track.
A train, hopefully.
The power supply will depend on where the track is. Now, you've got three options. A track where there's no main supply, a track where the power is not guaranteed, and a track where the power is guaranteed.
Aha!
Now,
Feigning interest.
Starting from the last first.
Yes, of course, that makes sense.
So, where we've got a guaranteed power supply, we use 865 and 867 feed sets, or the likes of the R4B.
Well, that's where there's guaranteed power supply. So what about where the mains power is not guaranteed?
Well, it's not guaranteed.
Yeah, you know, like where we have to use battery chargers to keep the batteries charged up fully. You know, when the main supply fails and we need the batteries for our backup.
Well, as you said, we use battery chargers. But also secondary cells.
Ah, the secondary cells, of course. Yes, secondary cells. The batteries can either be primary or secondary.
The early 867 feed sets had an adjustable resistor of sorts with a 3 and 4 ohm ballast settings. Now, the new style can only be adjusted for the length of the feed cables.
So what makes a long and what makes a short cable?
Well, it's not exactly how long, but it's how much loop resistance there is in the feed cables. Now, if the cable resistance is over 2 ohms, the green wire goes in the L block. If it's less than 2 ohms, it goes in the S. You have to make sure the input voltage is set to the right tappings.
East Rail 23 to East Rail 22. Are you receiving? Over.
2-3 receiving, over.
Can you take point 3 out of the feed can, please? Over.
Yes, will do. 2-3 to 2-2.
Receiving.
Yes, have taken point 3-8. We now have 5.7 in can.
Thank you.
East Rail 23 to East Rail 21. Are you receiving? Over.
Receiving you, Roger.
Hello, Mick. Can you set 6 mics in your can, please? Over.
Yeah, will do. Done that, Roger. You've got 6 mics in the can.
Yeah, cheers, Mick. Thank you. Phew, that's great, isn't it? 0.8, 90-degree phase angle.
East Red 23 to East Red 22. Do you receive? Over.
2-3 receiving, over.
Can you take point 3 out of the feed can, please? Over.
Yes, will do. 2-3 to 2-2.
Receiving.
Yes, have taken point 3-8. We now have 5.7 in can.
Thank you.
0.7 on the meter, 92-degree angle. East Rail 23 to East Rail 22. Are you receiving? Over.
2-2 receiving.
Yeah, hello, Rog. Can you put your can to 6.3 mics, please? Over.
Understood, Rog. 2-3 to 2-2.
Receiving.
Yes, we now have 6-3 in can. Over.
Thank you. 0.9 on the meter, 88-degree angle. 23 to 22. Over.
2 receiving.
Yeah, that's no good, Rog. Put it back to 6 mics, please.
Three to 2-2.
Yeah, receiving.
Back now to 6 mics.
Yeah, thank you. Okay, let's try putting 0.3 in the feed. East Rail 23 to East Rail 22. Are you receiving? Over.
2-2 receiving.
Yeah, hello, Rog. Can you put your can to 6.3?
Yes, okay. 2-3 to 2-2.
Receiving.
Yes, now have 6.3 in the can.
Yeah, cheers, thank you. We've got 1.1 volts on the control now and a 78-degree angle. Let's try a drop shunt.
0.9, 0.8, 0.7, 0.6, 0.5, 0.4.
Down. 0.4 drop shunt, that's a little bit low and the control volts are still low. East Rail 23 to 22, are you receiving? Over.
2-2 receiving.
Yeah, hello, Rog. Can you put another 0.6 in the can, please?
Yes, okay. 2-2 to 2-3.
Yeah, receiving.
Yes, I've put 0.6 in. We've now got 6.9 in the can. Over.
Yeah, thank you, Rog. 1.25 on the relay and a 73-degree angle. Let's try another drop shunt.
0.9, 0.8, 0.7, 0.6, 0.5, down, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7.
East Rail 23 to East Rail 22. Are you receiving? Over.
Yes, 22 receiving.
Yeah, hello, Rog. Have you got your full set of readings there?
Yes, Roger, all ready to go.
Yeah, okay then. What's the power supply?
Local volts 112.
Capacitor value?
6.9.
Volts across the capacitor?
Volts across capacitor 275.
Current to track?
Current to track 0.55 of an amp.
Voltage to track?
2 track 155.7.
Voltage across the rails.
Cross rails 2.67.
And the volts across the auxiliary coil.
Coil 152.
Right, thank you. Over. Right, volts across auxiliary coil 146.4. Volts across the rails 2.58. Volts to track 148.8. Current from track 0.41 of an amp. Capacitor value 9 mics. Volts across the can 164. Control volts is 1.25. Local coil 112. Phase angle 73. Control resistor is 100%. Drop shunt is 0.5. And the pickup is 0.6.
Well, the purpose of us coming here today is to work on BH track on the Down Slow here at Albrook. We should be doing a full test on it actually. For that purpose we've got a possession. We've actually got a juice possession as well, so the current is off. The Down Slow is closed. The Down Fast will be open to traffic, so we can expect trains at line speed, which is 90 miles an hour. Before we go anywhere near, can I see everybody's track safety cards, please? Colin, Rog, Dan, Brent, yeah, fine. Oh, and also your locate card, because you'll need that, because you'll probably be the lookout.
Right,
so
okay.
fine, that's okay. Yeah. Also, Colin, have you got yours? Because I'll probably appoint you to locate for Roger's team. Yeah, in date, fine. Okay, thank you. Our lookout, Brent, if you can be a lookout, please.
Yeah.
And have you got your method of warning?
Whistle.
Whistle, yeah, fine. Give it a quick Yep, fine, lovely. Good, that works. Yeah. Now, to get to the site, we're going to walk up adjacent to the down slow, and clear of the down slow will be our place of safety. So we won't require to cross the track at all. Hazards, there's one or two bits. Communications, we've got our cell nets as usual. Also, I believe we've got radios.
Yep.
Just like to give them a try, see if they're live.
Testing 1, 2.
Yeah, that works.
Yep, okay.
Sounds good. Right, okay. And also, if needs be, on the other side of the track at the relay room there, we have got a dial phone also available if we need to get in touch in a hurry on a direct phone. Okay. Now, Rog, Colin, you'll be going up to the relay end. So if you can be in charge of that, Rog, please. Up there, have you got a badge? Yeah, fine. Okay then. Thank you, gents. We can make a move.
In the usual method of traction return using 2 running rails, the current must be balanced between the two if the track circuit is to function efficiently. If it's not evenly split between the rails, the system is unbalanced, which affects the track circuit. That's why we say that the interaction between DC traction and AC track circuits is dynamic.
Good connections are essential, which is why they are checked during the Service A visual inspection and tested in the full test. The balance between the rails must be maintained to within 5%, or there could be a track circuit failure. Because the system is dynamic, you could find that the fault is not in the track you're called to work on, but in another one between you and your adjacent TP hut and substation.
Inside the impedance bond, you'll find auxiliary coils and traction coils wound around an iron core. The traction coil is connected to one of the running rails, and the other, wound in the opposite direction, is connected to the other rail. If the traction return current is balanced, as it should be, the magnetic flux in the iron core will be 0. Any unbalance could result in a net flux in the iron circuit, interfering with the AC track circuit current flowing in the auxiliary coil. The result would be an AC short circuit between the rails.